Hi, my name is Jonathan. I'm a PhD student in chemical engineering at Rutgers, and today I will talk about my research, which is based on the decomposition of chemical warfare agents. If you would like to see what our research group is focusing on, follow the link below so that you can go to our website, get more information. What are chemical warfare agents? They are lethal compounds that have the potential to target multiple subjects at once and considered extremely dangerous. Chemical agents are commonly divided into several categories, such as blister, blood, nerve agents, and other based on their mode of action. Blister agents, for example, are oily substances that act via inhalation and contact with skin. They affect the eyes, respiratory tract, and skin, first as an irritant and then as a cell poison. As the name suggests, blister agents cause large and often life-threatening skin blisters which resemble severe burns. And an example of a blister agent is sulfur mustard. Blood agents are distributed via the blood and generally enter the body via inhalation. They inhibit the ability of blood cells to utilize and transfer oxygen. Thus, blood agents are poisons that effectively cause the body to suffocate. An example of a blood agent is hydrogen cyanide. Nerve agents acquired their name because they affect the transmission of nerve impulses in the nervous system, which lead to muscle paralysis and eventually death. Current technology for the protection against these agents consists of activated carbon suits, which absorb the agents and trap them in the suit. Now, if you're interested in adsorption processes, check out my colleague's video on molecular adsorption on porous materials on this link. Now, the problem with this technology is that it does not neutralize these dangerous compounds, such that a soldier exposed to these agents in amounts higher than the suit can absorb are at high risk. Therefore, we propose new technology to address this problem. We propose to use a protective layer applied at the surface of the soldier's uniform that will not only absorb but decompose these active agents into non-toxic compounds to keep our soldiers safe. And here is how it would work. We would have a two-layer membrane in which at the surface of the outer layer we incorporate a class of active nanoparticles called polyoxymetalates or POMs. They are capable of decomposing agents by using oxygen available in air to provide an oxidation reaction. In the inner layer, we incorporate another class of active nanoparticles called metal oxides. These are inside the second layer of the membrane and are able to decompose the agents by using the hydroxyl groups or OH molecules available in the water inside the membrane to provide a hydrolysis reaction. In either oxidation or hydrolysis, the role of the catalyst is very important as it provides an attraction center at which molecules adsorb and can permit reactions to occur that would otherwise not happen without the catalyst. Imagine that you have to go to a meeting in a building that is 30 floors high and it happens that you have to go to the 30th floor. Think of the energy required to go 30 floors using the stairs. It would be quite exhausting. But if you use the elevator to go to the same floor, you will not even break a sweat. And this is what a catalyst does. It reduces the energy required for a reaction to proceed into its products. Let's talk about the hydrolysis reaction. When sarin is adsorbed at the surface of the metal oxide, it reacts with water in such a way that the hydroxyl group of water attacks the phosphorus atom, forcing the fluorine to leave and react with hydrogen to form hydrogen fluoride. This brings the intermediate product called isopropyl methylphosphonic acid, or IMPA. Water reacts again with IMPA in the same fashion as the previous step, forcing the isopropyl group to leave and react with hydrogen to form isopropyl alcohol or rubbing alcohol. Yep, the same one you use when you want to disinfect a wound. The resulting product is called methylphosphonic acid and it's considered non-lethal. Now, for the oxidation reaction, say you have a sulfur mustard molecule. When adsorbed at the surface of the polyoxometallate, sulfur mustard reacts with oxygen to produce 2-chloroethyl sulfoxide, which is considered non-lethal. Now consider a potential hydrolysis reaction at which the chlorine atoms are forced to leave as the hydroxyl groups attack again at both ends of the sulfoxide molecule. This reaction yields a thiodiglycol sulfoxide, which is even less toxic than the previous product, this along with hydrochloric acid. Therefore, if we get to implement this technology on military uniforms, chemical warfare agents can be neutralized before any harm can occur to a soldier. This way, we make sure that all wearing this technology are protected and safe. This project is funded by the Defense Threat Reduction Agency of the Department of Defense and supported by Rutgers University. Thank you for watching, and below is the link to our research website for more information.